Modern airliners can cross entire oceans at nearly the speed of sound. They fly higher than clouds, higher than storms, sometimes over 11 kilometers above Earth. So here's the question. If airplanes can already fly that high, why don't they go even higher? Why not 50,000 feet? Or 60,000? The answer comes down to a dangerous invisible limit hidden in the sky. At first, flying higher sounds like a perfect idea. Higher altitude means less air resistance, better fuel efficiency, and smoother flights. In theory, airliners should keep climbing higher and higher, but eventually the sky becomes too thin to support normal flight. And that's where things become dangerous. Commercial jets usually cruise between 30,000 and 40,000 feet. That's because the air up there is much thinner than at ground level. Thin air creates less drag. Less drag means lower fuel consumption, higher efficiency, and faster travel. That's one reason modern airliners spend most of their journey at high altitude instead of lower levels. Higher flight also helps aircraft avoid turbulence, weather systems, and crowded lower airspace. So naturally, airlines want to fly as high as possible. But there's a problem. Airplane wings need airflow to generate lift. Jet engines also require oxygen from the atmosphere to operate properly. As altitude increases, the air becomes thinner and thinner. Eventually, there isn't enough dense air for the wings and engines to work efficiently. The airplane must fly faster to compensate for the reduced lift. But there's another problem. At very high altitudes, the margin between stalling from low speed and losing control from high speed becomes dangerously small. Pilots call this the coffin corner, and this is one of the most dangerous regions of flight. At extreme altitude, an aircraft has very little room for error. Fly slightly too slow? The aircraft can stall because the wings stop producing enough lift. Fly slightly too fast? The airflow around the aircraft can become unstable as it approaches critical Mach speeds. That means the airplane is trapped inside a very narrow safe speed window. Sometimes the difference between stall speed and overspeed becomes incredibly small. This is why commercial aircraft cannot simply keep climbing forever. The higher they go, the more unstable and dangerous flight becomes. There's also another major issue. Humans cannot survive at 40,000 feet without pressurization. The air contains far too little oxygen. That's why airliner cabins are artificially pressurized during flight. But the higher the airplane climbs, the greater the pressure difference between the inside of the aircraft and the outside atmosphere. That places enormous stress on the fuselage. Flying significantly higher would require stronger aircraft structures, heavier materials, and much more complex engineering. And heavier aircraft reduce efficiency. Interestingly, some military aircraft can fly far above commercial airliners. Aircraft like the U-2 spy plane operate at extremely high altitudes, but they are designed specifically for that environment. They carry fewer passengers, use specialized wings, and operate under completely different flight conditions. Commercial airliners are optimized for efficiency, safety, passenger comfort, and fuel economy. Not extreme altitude. Around 35,000 to 40,000 feet is considered the perfect balance, high enough for fuel efficiency, smoother air, and long-range travel, but still low enough for safe engine performance, stable airflow, and manageable cabin pressure. In other words, modern airliners already fly near the ideal altitude for commercial aviation. Going higher would create far more problems than advantages. So why don't airliners fly higher than 40,000 feet? Because eventually the sky becomes too thin for safe and efficient flight. The engines struggle, the wings lose lift, cabin pressure becomes dangerous, and the aircraft enters one of the riskiest zones in aviation. 40,000 feet isn't a random number. It's the result of decades of engineering, physics, and the invisible limits of Earth's atmosphere.